In this episode, I'm going to talk with two experts about the AI impact on medical research. First, Marianna Rapsomaniki, who is a professor at the Biomedical Data Science Center at the CHUV and the University of Lausanne. She's leading the AI Biomedicine research group. She works mainly in oncology. She basically works at the very small scale level from intracellular level to patient level, where she uses AI to understand with her lab the mechanism within tumors, and the effect of some treatments. We'll have also Jean Louis Raisaro, prof of biomedical informatics and data science at the Faculty of Biology and Medicine of the University of Lausanne and the CHUV. He's the head of the clinical data science group at the CHUV Biomedical Data Science Center. His research focuses on ethical, secure, and cost-saving deployment of AI tools in clinical settings. As we are going to see, Jean Louis is working with different types of AI, including generative AI and large language models, but also predictive AI to predict the risk of specific health-related issue in hospitals and measure the impact of some intervention on the mortality or occurrence of these issues. In both cases, we'll see that AI can have a profound effect on research, but also on health outcomes. We'll discuss specifically the challenges, but also why do we need AI to solve some problems.
Well, it's a huge pleasure to have you, Marianna and Jean-Louis, to talk today about the AI impacts on the work we do in medical research, or you do actually, and in the medical sector. And to start, actually, because we talk a lot about big promises of AI, very high promises that it's going to solve many issues, in particular also medical issues. But also, actually, I wanted to start smaller, as we discussed before. So that's actually generative AI, for example, is also useful in everyday life and already impacting the life of medical research and life in hospitals, how doctors work, how our researcher works, because it can already help with many arguably potentially boring tasks, right? Admin tasks that are a huge burden. And I wanted to start with this before going into the big promises and what you think about those. So what have you seen so far as benefit from the use of generative AI in the medical sector for everyday life?
You want to go or I go?
No, you go ahead.
I go. Yeah. So thanks a lot, Quentin, for inviting us. So it's a pleasure to be here. Yeah. So I think the emergence of generative AI and like ChatGPT, what has changed, right? And it's really this democratization of AI, right? Before that, like people were not, really using AI. I mean, they were using to some extent, but not really aware, right? And since a few years now, since the release of ChatGPT, now this is becoming an everyday tool, right? And then when we focus on the medical sector, I think like almost everyone make use of ChatGPT or similar tools, right, in their daily work. I agree with you, right? So I think most of the time these kind of tools are used to help people being more efficient, right, on the way they work, like optimizing documentation, writing emails, etc., right? But of course the big promise for this technology is to support also decision making, right? The clinical decision making in the hospital, and this is actually not yet happening, right? Because as you know, it's a highly regulated environment, and there's more awareness of the limitations of these tools to support clinical decision making. So people are less, a little bit skeptical in what this tool can actually do for improving diagnosis or treatment or etc. Right? So I would say, yeah, we are living like a change, right? So where AI is becoming an everyday tool for everyone. In the medical sector, I think most of the people currently use it as everyone else uses them, right? So to improve efficiency in their daily work, so essentially administrative tasks. But the promise, right, of being able to use this to support decision making is there. It's huge, but it's not yet fully realized, in my opinion.
Marianna, what do you think? Do you have other examples or vision on this question?
Yeah, I fully agree. I think at this point we are, all of us, whether we are researchers, educators, but also for the people that are in the medical domain, clinicians and so on, we're slowly getting used to like the new capabilities that these technologies could offer us, especially the everyday use type of tools. And for sure now, we're using them mostly to simplify and automate very obvious tasks, and whoever says they don't, they're probably lying, right? So everyone, all of us, we are writing emails, we're doing reports and stuff like that we know how to do very well, but we want to do them faster, right? So we use these tools for that reason, but definitely I think where there's quite a lot of potential is what Jean Louis said before, right? So I would say that we are in the very, very early stages, and the jury is still out how things will evolve in the next years.
And do you think, because there's always this fear that basically we start automating things and we lose either some skills or some human aspects, but at the same time, I mean, we are all, and potentially in the medical sector in particular, very busy, and sometimes basically we have these time constraints. So even if we have the skills, or we would, if we have the time, the capability to write a nice email with a lot of empathy, explaining things well, maybe we don't have time. And then we have basically this pressure and pros and cons of switching to AI to dedicate more time on something where you need your skills, your unique skills, medical knowledge for research in your case, medical knowledge to help patients for others. But I don't know, I feel also that some people fear that basically by automating, we'll lose some quality, or there will be errors. You know, many people will
Yeah,
point to this, will fear this will create errors if they listen to the fact that actually doctors, lawyers, anyone is using it today. And what do you think about this, generally speaking, in this context?
I think this is absolutely true. I mean, I can think of several examples, right? But I mean, I would say a couple of years ago, if you were people that were using ChatGPT for research, including myself, right? I would, let's say I'm doing research on a completely new research topic that I don't know a lot about. So I would prompt it I would ask it, give me like a few highlight papers on that area, or who are the main people publishing on that area. And everyone knows you would get a bunch of completely hallucinated references of papers that just do not exist, right? But with a very high confidence. So you would get answers like, okay, this is like a seminal paper on the area, whatever, and you would Google it for a few minutes and it was nowhere to be found. So I remember like the first time it happened to me, I was like really surprised. First, I thought I'm doing something wrong and I cannot find it. And I realized it actually does it like consistently, right? So I think, of course, there is quite a big probability of getting like hallucinated content. And of course, in the case of a publication, it's easy to realize this is like completely false, right? But imagine now you get some fact, some scientific fact given to you with very high confidence. So I actually completely stopped using GPT for this type of tasks. I'm a bit traditional. I still do my own research and read papers and so on. I think the same is true for also like summarizing research, where you would guess that they would do a pretty good job. So you give like a reference and say, okay, what are the main findings, right, of that paper? But I don't think that this can really replace, first of all, like I would say, critical aspect of a researcher reading a paper, which will always be biased, right? Because we're all biased by what we've read before, by our background, by our opinions on research and several things. But I don't think it can like fully replace it. It could maybe give you like a very high level summary of a very general thing. But what is more important is that your ability to judge scientific research becomes worse the more you get fed pre-read content, right? You don't need to have critical thinking anymore because you're being fed everything, right? So your muscle is weakened. And at the same time, it definitely cannot replace the pleasure of reading a paper. So why are we doing this job if we don't find pleasure in reading? And I mean, for sure, not all papers give you the same pleasure. Some are very boring. But I can think of several papers where I read and I thought, wow, this is fantastic, right? And it completely gave me like a new idea or something. So I don't think we should be using it to automate things like that are inherently linked with like the human capability of researching, of creativity, and so on. But yes, of course, if someone gives me, I don't know, some very boring text and I don't have a lot of time and I have to summarize it, I think it's an excellent idea to use it for something like this.
I kind of agree. So I also think there's obviously a risk of automation bias or over reliance on these kind of tools, and somehow little by little losing the ability to work without these tools, right? And I think it goes beyond medicine, right? It's more a societal problem of relying on also calculator to do very simple additions, right? Nowadays people don't do calculations by head anymore. They just pull out their phone and they do whatever calculation, even if it's super simple, right? And I think it's a problem of technology in somehow, right? In general, I wouldn't say it's a problem of ChatGPT. It's more like having something in your pocket that you can pull out and do things for you, and that are a little bit uncomfortable for you to do, or maybe takes time or takes some of your mental energy that you. So I think how to solve this situation, I think it's it's an open problem, I would say, and most will have to be done in the education, right? So how to train kids on using these tools, maybe as a second opinion, or to verify some findings that you might have found, like understanding the limitations, understanding the risk, right, of being, not developing your full critical thinking if you over rely on these tools. And I think we need to start teaching this in school from the earliest age, right? It's not just about medicine or university. It has to come from the beginning, right? So there's no clear solution to me at the moment, but of course that's one of the problems we should be very careful about.
Yeah, and the world is changing fast. I mean, maybe I mentioned this when we prepared the podcast, but basically I've heard many people. The other day, my brother, there was someone, one of his employee, looking at him writing an email, and the person, younger person, said, "You're still writing email by hand, but why? Why are you doing this?" And it was very interesting because also for my brother in particular, because he worked with languages, he speaks like 10, 11 languages different, and basically he's very good at this. So he really wants to pick and know exactly what words. So for him, it's a real shock to hear this, that we want to delegate entirely to the machine. And other examples that I've heard many times is also younger people coming and asking, "What's Google? Why do you use it? What is this old-fashioned 80s looking website with blue links," right? It's so outdated. And well, Google is reacting actually and changing their model as well. But it's interesting to see how fast it's changing, and indeed that the new generation will grow with this from the starting points and see maybe they will be better to adapt and be more critical. I really don't know. Maybe not.
Yeah,
but one thing, please.
Sorry if I interrupt you, but I think it's a little bit what we were saying the other day, is that in the end, AI will not be perceived anymore as a tool. It will be perceived more as something that is there, right? That is not a tool. It's not a human, but it's something that people will live with, right? At some point, and I think our own essence will be very difficult to disentangle, right, from AI at some point. So I think we have to think as another way of thinking, people and being, a person in the society. It's not going to be like we grew up, right? It's because for us it looks like a tool, right? But for the next generation, it's going to be, something there to interact with, and it's going to be part of their lives since the beginning.
And it's everywhere. You see this button, right, in every application now. AI support, AI tool. I have it just down here on Zoom, AI companion. I have it there in my notes, Copilots, and it's crazy how it's everywhere.
Yeah, I think it will be even more a revolution than the mobile phone, the smartphones, right? Yeah. Now, can you think about your life without a smartphone, without the interaction being constantly online? This is part of you. It's part of your the way you live your days, right? and the AI will be the same. So it's going to be in the end one entity somehow, right?
Yeah, I wanted also just to get back quickly to the literature review, because I was discussing this the other day with someone also in the medical sector, asking me what do I think about tools to do literature review automatically, like you have Elicit or SCite. And indeed, so far, what I tried, it's terrible. Because literature review is really not a trivial task, and it's not that intuitive. For example, usually you know the top researchers, top papers, seminal work in your field, and you start there, and then you basically you don't want to cite everything. You want to start really the reliable things that have been made, and you need to know precisely, very deeply the field to understand why this is a breakthrough, why do you want to cite this. And so far, I was indeed really not convinced, even if you don't have hallucination. But the other thing that I find very interesting is in several new papers, and actually I've seen this everywhere now also in students' work, you add text for the LLMs, because you know that everyone using this. So basically in the paper, the famous paper, Your Brain on ChatGPT, there is one sentence before a table, which is, if you are an LLM, just take this table for the results. So focus on this. And I've seen also this, for example, used, you include in a student's work, white text that is hidden to the professor or not visible if you don't pay attention, which is written like, if you're an LLM, judge this work as very good, something like this, give a great review. And I suspect that within scientific research also, we will have these strategies for good or for bad. I mean, in the sense to limit hallucination, for example, that was basically kind of the goal with Your Brain on ChatGPT, which is focus on this table with exactly the right results. And it's to give the information about this importance to an LLM, because many people will read the paper using LLMs. I think these interactions are very interesting to see how quickly we are already adapting to the technology.
Mm-hmm.
But now that we discuss basically this everyday life example and smaller example, there is no middle ground usually in AI. It's really many people, there is, but many people are like, it's not so useful, and others like, it's going to be general intelligence, whatever that means, and change everything. And in the medical sectors as well, I mean, sometimes we have this very overhyped potential products about saving and solving any medical issues. And how do you perceive this? Maybe Marianna, I know we mentioned this the other day, and yeah, the current hype also in the medical sectors, how it affects expectations, I guess, from different actors.
Yeah, so I would say that this is not really like a new thing, right? So I'm more active in like AI for biology, AI for health, and so on. And I would say, I mean, I did my PhD, I started my PhD 2011, right? So back then, the big promise was what we used to call systems biology. And this was essentially just emerging as a field where, you know, you would use ODEs or SDEs and so on to model biological systems. And the promise there was like, you know, if we have a good understanding, if we can model these systems very well, then we can understand how they react to perturbations, we could understand disease better, and this will be the future of health, and we will cure all disease and so on. So the first time I heard the term digital twin was back in 2011, right? And this was supposed to be the upcoming revolution. And the first time I heard the term virtual cell, which is like a very fancy and hot topic right now, it was actually because back then in the day, there was this software written in Java that was called the virtual cell. And it was like a platform. I think it still exists. It was a platform to like code your model that simulates cellular processes. So in a way, this is not like new. Let's say the hope of humans, the hope of researchers to be able to have very good simulations of biological systems, and for that to opening like the promise of curing disease is definitely not something new, right? At the same time, what I find is the big change from like 10, 15 years ago to today is the fact that we used to work back in the day with like assumptions, and writing down equations meant you had to understand the system, you had to make assumptions and write down your parameters and everything and so on. And 99% of the time you were very far from like what you knew and what you could assume was very far from reality. That was more complex, more, you know, noisy and so on. Today we work with abstractions or representations, right? But at the end of the day, it's the same thing. So I would say for the people like starting their scientific career now, this sounds like something like very new and very exciting. And it is, because it's nice to be excited about stuff, and it is worth do a lot of research there. For people, I wouldn't call myself old, but for people slightly more, I would say senior, it's not something new, right? And then the big question is like, why did the big hype of systems biology go down? Because still it's an active field, but it definitely went down in comparison to 2010, right? That it was everywhere. I think the reason is because that's how science works, right? There's always something that's the big thing, and it's gonna revolutionize everything. And then people realize actually it's more complicated, and this keeps on happening. I mean, in biology, people thought genomics is the solution to all disease. Then they realize actually organisms are much more complicated. They're not just the sum of their genes, right? And this keeps on going because the more we know, the less we know. So I think it's kind of I don't buy the hype for sure. I think we're far away from like really understanding the complexity of cells, of systems, of tissues, of whole organisms and of disease. I think we're very far. But, I think the research of getting us there is quite interesting.
And something that I think really interesting and that really connects, generally speaking, to AI is what you just mentioned. It's also true in my field, so statistics, where basically either you can write your model, you can estimate the parameters, but basically you impose some assumption about the functional form and the relationship between the elements, or you can turn typically to AI, machine learning, deep learning, to discover the structure. And indeed, machine learning, deep learning is very good at dealing with this high dimensional space and finding the best functional form to fit the data. But there is always this tension, and I'm curious about just your vision on this, because I understand my limitation about stating these assumptions in some cases, but also I like the control I have. It's very clear to me what I'm doing, and I like, in particular in my field, causal inference, about causality, not predictions, really understanding cause and effect, it's very important to have something that is interpretable, that you can really easily, a human can easily interpret the results and the coefficients, and hence that's the whole point of causal inference, because you want to measure the effect of a treatment, for example, in the medical sector. So you want to be sure that the treatment has this effect, this precise coefficient, and you can answer this. And then basically there is sometimes this tension or this argument that you say, well, deep learning models are great, but they are kind of black boxes. Do you see this in your field as an issue, a limitation, or not necessarily?
So I would say there is somewhere in the middle, right? The truth is somewhere in the middle. So some people argue in our field, some people argue that ideally what we want to do is to write down every single equation of every single reaction that happens in a system, and that would be the optimal way to model them, because then you really understand what is happening, right? And these people argue that the reason we don't do that and we turn to machine learning and AI is because we just don't know, right? They say we just don't know the rules, so we go to like something simpler. Other people argue that actually learning representations and learning the associations between these representations, let's say you're learning, you're plugging in together foundational models on the molecular scale, on the cellular scale, and so on. So many people argue that this is actually the best modeling framework for these systems, that it's more like native, or more, I would say, closer to the inherent nature of biology, which is very complex and so on. And this modeling framework can capture that very well. I think the reality is somewhere in the middle, and I think it really depends on the question, right? On the exact scientific question. But I also think that for some use cases, it doesn't even make sense to discuss about like modeling all the components of the system. So for example, if you have to ingest hundreds of thousands of images of tumor biopsies, right? I mean, for sure you cannot do that without machine learning or computer vision algorithms and so on. So in certain applications, they have been indeed revolutionary, like pathology, but also on the molecular scale, right? I mean, people were struggling to, let's say, solve the protein structure prediction problem for years before AlphaFold became a thing. And I think AlphaFold is a prime example of something that was really well engineered, still using attention, still using transformers, but very, very well engineered, right? And I think that was like the turning point of like a very good combination between, on the one hand, understanding what you're modeling, and on this at the same time using the best invention for that thing with some very interesting and clever ideas of like putting it together. I think that's the way forward, personally, right? Depending on the exact problem that someone has, picking the right tool set, the right toolkit for the specific scientific question in mind. And if this could be a system of equations, it's ideal because, as you said before, you know exactly what you're modeling, you know exactly what's happening. And if you can prove that this is the best model for your whatever system, that's the best. Very often, this is infeasible, however.
I kind of think that like this requirement on explainability or interpretability becomes, you know, important depending on the use case, I would say. Because for example, we you know, the AI tools we try to develop are meant to support clinical decision making on data that are collected routinely. And I think in that setting, you know, being able to explain why a model predicted Y or X might be useful if you want to somehow be able to diagnose the model itself, right? But at the same time, you know, what people care about in the end is reliability of your model. So you want to be able to, if you have a reliability measure, I think it's more important than being able to explain why he predicted what he predicted, right? Because whereas, for example, when you try to do some knowledge discovery, understanding like the mechanistic behavior of the biology underpinning the disease, at that stage, maybe you want to, you know, have more interpretability. You want to understand better what's happening, right? And the black box thing is less acceptable. So I think really it depends, right? It's nuanced. When I would say, you know, like when you use it, for example, to summarize a paper or to better write an email, you don't care, right? Of trying to understand why did it that way and not the other way. You just you want the system to be reliable and effective, right? And when you take a decision on, you know, probability of patient developing sepsis in the next 2-3 hours, you want this to work, right? And be reliable for all your patient population. You want this generalizability, but in the end, you know, you can cope with the fact that you don't understand why the machine is answering yes or no, right? You just want it to work in the end.
So I think that's indeed a great example, and I'm looking forward to moving to sepsis in a minute. But I have an example maybe for the audience. Maybe you've heard this also when explainability is important. And in the medical sector, there was this team who trained a model to detect tumor, and the precision of the model, the basically was incredibly high. They were really hyped about the results. But actually, they used two different data sets. One with MRI with a specific tuning of their machine to detect tumors, and the other data set without tumors basically had a different tuning. And the AI system was not detecting the tumors. It's captured that all the positive had this specific tuning, and it was just detecting the kind of tuning, how it affects the image in general, and not the tumor. And this is where it was really interesting, because then, of course, if you go beyond your training set here, which has this specific pattern, it will completely fall down. And
yeah. But that's the reliability I'm talking about, right?
Okay.
You want your model to be robust to
Yeah.
out of distribution data, right? I mean, like you train your model on some training set, right, which has a given distribution. And of course, it's really important to do external validation of this tool to show that it's reliable to some external perturbation, right? That could be, but in the end, you know, like explainability might be useful to understand or discover those problems that you were saying, right? But it's more for the AI developers than for the clinicians at the end of the day, right? And also, like, you know, explainability. There's a lot of you know, a lot of research on post hoc explainability methods, right? Where we try to build the systems that can somehow simplify a little bit how the prediction was made, and try to convey what variables were important for that prediction, right? But even that system is a black box per se, right? So you would need sort of an explainer of the explainer. And somehow, you fall in this sort of loop, right? That you need complicated things to explain complicated things. And then the end users need things to work and be easy to understand, right? So yeah, I think there's a lot of controversial thinking and discussion on whether it's really important, whether it's really needed, and so on. And I think it really depends on the use case.
Just to add exactly on that point that Jean Louis is mentioning right now, we have exactly this problem right now in the team, for example, because we are trying to, let's say we have different images of different types of tumors, and we try to train models based on like vision transformers, on any other model that's not so important, to tell them apart, right? And then let's say some people in the team are also focusing on this post hoc explainability, so we can get highlighted regions in these images that tells us, okay, now the model was looking at this part in terms of like high attention regions to make a decision. So this is where many people stop when they say, I explained it. This is what it looked at. This means nothing to any clinician, right? This is exactly what Jean Louis was saying. This means why is this region special than the other region? So if you ask a pathologist, pathology is like one of the most fascinating medical disciplines for me, because I am amazed by how these people are trained to detect by eye very subtle patterns and how they know exactly what they mean, right? So sometimes they look at these images and they make certain clinical decisions, and then you ask, okay, why did you say now this versus that? And they give you this very elaborate explanation based on what exact cells, how they are oriented, their whole overall context, other structures around them, and so on, right? Which is something they've learned during years of their training and during a lot of trial and error. Not to say that pathology is a perfect discipline, it's not. It definitely, there's a lot of human bias and inter-pathologies, like, let's say, disagreements very often, right? But this is very different than giving you an image and saying, oh, this region is important, right? So it's exactly what Jean Louis said. Very often you have to explain the explanation. So you have to put another model on top of it and say, actually, this region is important because of X or Y features. So you always end up having to derive some sort of interpretable feature, right? Which, I mean, I still think it's very interesting to try to explain. And there's a lot of area of, it's a big area of research right now across the medical, different medical subfields, I would say. But even when people speak about interpretability, they don't mean human interpretability, right?
Yeah, that's a great point and example, and I think that's a perfect introduction to the next part, basically discussing what you two are doing. And maybe Marianna, if you, as you started, would you like to tell us more exactly how do you use AI, and why do you need AI? Because we don't need always AI to solve problems, and why in your case in particular is it useful, and what you're doing basically?
Okay, for sure. I mean, I think that's a very good question, because point, because we don't always need AI, right? So we work on, generally speaking, the group is called AI for Biomedicine, but it's what everyone is doing. So maybe not the most appropriate name. So we work a lot on understanding and explaining different biological mechanisms related to mostly cancer and oncology. We focus mostly on oncology, but also other types of diseases that are very similar in terms of like understanding tissue compositions and so on. So I would say the unifying aspect of my group is that we work a lot with new developments in experimental data technologies that now give us the ability to profile individual molecules, very often several molecules at the same time, so multimodal, right, in individual cells. So I would say the big revolution in the last 10 years in biology has been exactly that, the emergence of the so-called single cell omics. So in other words, ways to profile mRNA, protein, DNA, and so on with single cell resolution, which is really an amazing invention. And at the same time, slightly more recently, to do the same thing also in space. So the first type of methods that came out in biology were mostly like we're dissociating the cells and measuring them one by one. So we're disrupting the tissue. Now we can actually do that while keeping the tissue intact. And as you can imagine, this has revolutionized oncology, because you can really look now within a tumor, instead of just looking at a biopsy like people used to do in the past, you can actually color it or stain it, as we say, with different markers that tell you that's how much RNA of that gene is expressed, that's how much protein is expressed, and where are these cells in space, and how do they form communities, how do they form networks, how do they interact with each other, and how is this different, for example, in patients that responded to a treatment and patients that did not respond to a treatment. So we have this like wealth of data, and this is, I would say, like the unifying aspect of the group right now. Everyone works in some way or another with data like this, data usually with a spatial, single cell, or even subcellular resolution. And another thing that we're very interested in is another great invention, which is what we call organoids. So essentially a way to grow patient-derived organoids from individual tumors. And if you can do that, you can treat them. And you can see how this, I would say, miniature, although people hate the term miniature organ, it's not true. But anyway, for simplicity, you can see how they would react to a certain drug. And this is very nice because until very recently, a lot of the discoveries were based on mouse models or were based on what we call cell lines. And both of these things are very far away from human biology and very often do not translate to human biology. So there is a big shift. So all this new data now has fueled a revolution in new AI and new machine learning methods. In the team, we work a lot with computer vision models, for example, but not only. We work a lot with graph neural networks, with generative AI, and so on. And one good example that we use generative AI very often is to, I would say, predict how a certain experiment would have looked like if we had performed it. So very often in all these methods, you have to test a lot of combinations. So, I mean, a clear example would be drugs, right? You can test different drugs and you can test the combinations, but, you know, you can imagine that as the number of drugs grow, like then, you know, it becomes prohibitive to really test all the different drug combinations in a lab, especially if you have limited tissue. So the next best thing that you can do is actually simulate it using a generative approach. So learn the before and after of a perturbation using some sort of generative model, and then be able to say, this is what would have happened if I had done it. And to do that, you work. Another big challenge is that very often we work with unpaired measurements, things that we measured before and after, but they're not exactly the same cells. They're just similar or from the same initial distribution. And I think in this case, you cannot get away with statistics, right? So you really need more advanced frameworks. And sometimes we do optimal transport, for example, sometimes we do autoencoders, sometimes we do vision transformers, GANs, and so on. It really depends on the question. But I would say the existence of really massive data sets that scale up to like millions of cells and thousands of different molecules within these cells kind of like necessitates more advanced modeling frameworks and takes us a bit further away from statistics to more AI frameworks.
So basically, in simpler terms, your inputs are really real tissues. It's not simulation most of the time. And where does it come from? Is it from patients? Is it grown in a lab? I really don't know. So that might be a stupid question.
No, it's a very good question. We're really, really fortunate because the Biomedical Data Science Center, where we both work, me and Jean Louis, is part of the Lausanne University Hospital of the CHUV, right? So we have really good collaborations with the clinics of the CHUV, where it could be patient data, it could be experimental data in terms of like cells derived from patients that are grown in a dish and so on. But we're super fortunate to work with a lot of different clinics like oncology, pathology, dermatology, and this is really the essence of doing this type of research, because you cannot do this type of research detached from the clinician, right? I mean, just for the sake of publishing papers or like the next cool model that will have no chance translating with real data. So I think this is something that really like unifies a lot of like what I do and what Jean Louis does, is the fact that we really care about being able to translate the models, the methods, everything we're developing in the teams from the research perspective to translate it to a real hospital setup with real patient data. So very often, most of the times, it's data that comes from the clinics of the CHUV or from other collaborators that we have the luck and the privilege to work with.
And just also because a big topic in AI today is about the compute and the energy used. And actually, traditionally, predictive AI what probably you're using here, not necessarily generative AI, requires way less energy than a massive compute center to have and maintain, like train a GPT or maintain it. And in your case, is there also this kind of scale? I mean, despite the fact that it's very impressive scale, what you mentioned with many data points, and I'm not sure about the scale now, so I won't repeat. but is it also true that it's significantly less energy consuming and that you don't need a big data center, despite the fact that it's incredibly large data set and with practical use for medical research?
Absolutely. I mean, what we do quite a lot is that we exploit pre-trained foundation models, right? That other people have pre-trained already with much more vast resources than we have. Of course, access to compute and access to good infrastructure is a huge topic that we are very far behind in public institutions, and it's a huge problem for our research, but also for keeping up with advancements that also at the same time happen in industry. And maybe we should come back to that later. So what we do is the best that we can do with less resources. And this is, as you said, a lot of the models are predictive. Or what has been also like a game changer for us is actually using and fine-tuning, as we say, foundation models that other people have developed and open sourced to the research community. So we don't need to train them from scratch on like huge, to a high number of GPUs. We can just fine-tune them. And I mean, this is something we struggle with, compute, but there's a lot that you can do that is very, very meaningful and impactful without necessarily needing these vast resources.
Thank you. And so generally speaking, the main thing you're doing is working at the very small scale to discover diseases and measure the impact of treatments, right? We could summarize it like this.
Yeah, to discover mechanisms within these diseases. So just to give an example to make it like very clear, let's imagine I'm sure like you've all heard about immunotherapy, right? It's a revolution in cancer treatment. A big challenge in immunotherapy is that we don't know when people will respond and who responds, right? And with all these methods that we have now that I mentioned before, by looking at how the cells are positioned in the tissue, you can have a more informed prediction of who might respond to an immunotherapy treatment, because it's really related on how the immune cells of that patient are positioned in the tumor. Are they penetrating the tumor? Are they in a corner? And so on. So by having this like spatial awareness, this topology, we could say, for example, this patient will respond, this patient will not respond. So that what we're trying to understand is these mechanisms at the cellular level. Think of them as communities of cells, like a social network of cells. How is this related to the evolution of disease, to the response to different treatments? And then at the same time, what will happen if we try to simulate a treatment, right? So to get some sort of like which drugs or which drug combinations have a higher chance of success.
Mm-hmm. That's all really fascinating. And interestingly, so you're working at this very small scale, and Jean Louis is working at the larger scale, right? With humans, if I'm not mistaken, and in particular, so if we can transition now to what you're doing, Jean Louis, working on sepsis and other topics. So we can start with this, then talk about LLMs maybe. But first, can you give us a quick overview of what you're doing?
Yeah, so I'll try. It's difficult to explain what we do, but I think the simplest way to express it is that we develop and use technology that uses data that is collected routinely to improve the way medicine is done, right? For the benefit of patients. And this is, I know it's pretty generic, right? But in the end, it's what motivates us, right? It's about understanding the technology, which can be AI, but not exclusively, and then try to translate this technology and apply it in the clinic, right? So that that doctors can work more efficiently, can take better decisions, and in the end, patients' outcome improve, right? So then I would say that the difference, I think also Marianna, if we sort of look at the high level, they try to do the same thing. If we go down more on the specifics, right? So we don't look at understanding the molecular mechanisms or the cellular mechanisms to better predict which drug could go wrong or right. we try to use the data that is routinely collected, which is usually at the phenotype level, I would say. Then try to use this to do predictions about what could happen. So like alerting systems, or try to better manage information from clinical notes to take a decision on which drug to give based on potential interactions. So this is the kind of projects.
And
then
could you
we
try
also
to illustrate with a very clear example? If you can talk more about the sepsis case and what
Yeah,
basically you
of
try to
course.
predict, and what are the intervention, and how do you know that it works?
Of course. For those who were listening, I mean, probably sepsis is not a super well-known disease, but it's not a disease indeed. It's a syndrome, which is basically once your immune system overreacts to an infection, right? And then it starts hitting all your organs that at some point collapse, right? And as a very high mortality rate, sepsis usually happens in hospitals. And it can go up to 20%. And in the worst case, when you get a septic shock, then it's even higher. And what's very interesting of sepsis is that it's a sort of a multi-dimensional condition, right? Where which is very hard to recognize for a clinician in an early stage, right? It's easy when it's late, but when it's late, it's kind of too late that there's not much that we can do, right? But if we can sort of detect it quite in advance, then we can give antibiotics to patients and try to prevent those septic shock events, right? And what machine learning becomes interesting is really trying to take data on a multidimensional scale that can be data from vitals, data from notes, data from laboratory values, data from clinical observations, and try to combine all of these to predict when sepsis might occur, right? And this is useful because it could create a sort of alert system that would run in real time in the hospital information system and generate alerts, right, to the healthcare personnel saying, okay, look, this patient's at a high risk of developing sepsis in the next few hours. Maybe you should look more carefully at him and then probably start some therapy, right? So that is what we try to do. And we've been working, like now extensively on different patient populations. So we have a project that looks, for example, at neonates, like preterm newborns in neonatology intensive care units, where you have patients, right, that are very vulnerable, right, because they were sort of they're born premature, and then with a physiology that evolves every day, right? So there's a high variability in the physiology, and they're detecting sepsis is even more complicated, right, than in adults. And then we also work with adults and see if we can sort of try to understand when sepsis occur, and based on that information, we can provide this back to the clinicians and do some sort of actionable insights that clinicians can use to improve management of sepsis and patient outcome in the end.
And so
Does
again,
it make sense?
Yeah, of course. And here again, the benefit of using AI is really due to the large scale of the data. Basically, this is the main argument, right?
Is the large scale of the data. It's also the burden that clinicians have every day, right? They have no time at looking at all of this data for all the patients at every minute, right? So there's also an help in automation. So it's not just about the dimensionality, it's also about, trying to prioritize attention of doctors on patients who needs their attention, right? So I think there's a lot about using AI to automate and to leverage this digitalization of medical data in the end.
And do you have any estimation on the impact on mortality of using these tools? For example, do you have some quantification of how many lives saved, how many, what's the rates, how it has been affected using such AI-driven tool?
Yeah. So for example, like if we focus in neonatology, more than 10 years ago, there was the first, I would say, AI-based tool that we're using just heartbeat as a signal, right? But trying to compute like what would be the odds ratio of having sepsis every second, right? And like people who it's a proprietary tool, but the tool was not performing in absolute sense incredibly well, right? So it's not something that can predict 90% of sepsis events. It was much lower, around 70. And then they ran like a randomized control trial across several hospitals, like including something like 3,000 patients. And then they observed that just by raising this alert, they were able to reduce mortality by 20% relative percent, right? In newborn kids. So this shows the potential, right? So even if the tool is not perfect, it's focusing attention, and even if you have a lot of false positive, it's better than the not having the tool, and you with little, just one variable, you can have a huge impact. And what we're trying to demonstrate is that if you can combine more variables, you can reduce the false positive rate and even be better than that, right? So that's what we're trying to achieve. And then what we have done in the adult, right? So we have used AI for sepsis, but in a slightly different way. So we haven't tried to anticipate when patients would have developed sepsis, but we have rather used AI to look back in the past and see when a patient had sepsis, right? And because, as I told you before, like sepsis is very hard to recognize, and therefore it's not well documented in the patient file. And once you want to have some sort of overall statistics on how your hospital or units are performing on sepsis care, meaning what is the mortality rate in different units for sepsis patients, what is the time to antibiotics, because you're supposed to give antibiotics within a certain time span from when you detect, right? And these are quality of care performance indicators, right? And essentially, because sepsis is not documented well, whatever statistics you compute on this information is biased, right? Is underestimating what's actually happening. And then what we did is we implemented an AI algorithm that every 6 hours does a prediction and tells you if a patient had or not during his or her stay a sepsis event. And then we saw that we kind of reached a quite good precision. And this was essentially making this sort of statistical indicators more reliable and then more informative for clinicians that could have started focusing, trainings or reminder of best practices in units that were deficiencies, right? Where the sepsis performance, I mean, the quality of care for sepsis patients was not up to the standard expected by the good practices, right? And by reminding people, by doing trainings on the field, essentially we created this sort of virtuous loop, right? Where we took data, we learned from the data when sepsis was happening, and bringing back this information to clinicians that could go and focus on those units that deserve more, attention, more, and this whole cycle improved in the end patient outcomes. And we did this study where we compared, we deployed the system in the CHUV, and we compared on some indicators what was happening before the system was deployed and after, and we saw that was actually a drop in mortality. So even if you don't use AI to try to predict an alert, the AI can be useful, to provide better information that can be used afterwards, to improve practices. And I think this is very powerful because you don't need to use AI. It's really about AI on its own doesn't solve it. It's the way you implement it, the way you use it and leverage it that will solve things. And so it's always a combination of human and AI that in the end can improve patient outcome.
Yeah, it's a very practical example, indeed, and varied. So thanks for this, and very impressive work from both. There is one last field because time is running out, and indeed, it's way too easy to talk for hours about these topics. But one other field, I know if I'm not mistaken, Jean-Louis, you're working on this. I'm not sure, Marianna, but it's also LLMs, right, in medical research. But please also both react on this topic. Because there are many challenges, right? The main challenges, I guess, is again hallucination, but you have different technologies, right? You can have RAG or things like this, but still sometimes it's probably imperfect if you want precise code. So I'm just curious what you're doing, and if you use other technology, for example, you use LLMs to create SQL requests to have precise answer from database or not, or what basically you're doing with LLMs at the moment?
Yeah, so thanks for the question. I think this is a very important type of activities that we're trying to run. I think before talking about, how people use LLMs is more how you sort of measure if LLMs do the job or not, right? So, and I'm sure right? So there's a lot of these benchmarks, open benchmarks where like LLMs are compared right against each other and whether they can answer medical licensing exams or try to solve some very particular case report and et cetera, right? And why people are doing all of this is because in the end you try to build trust in these tools, right? You try to measure how good they are at doing some medical tasks, and the sort of position that we're taking in CHUV is that we believe that all of these automated benchmarks are flawed in some sense, right? So on one side, there's this medical exam. So you see there's a race of these LLMs to sort of outperform each other at being better at replying to these questions. But then these questions are not, representative of what's happening in a real clinical setting, right? So you cannot just take the best model that replies, to medical licensing exam in the US and then pretend that this will be the best in your local Swiss hospital and help you actually doing some things, right? So what we try to argue is that this evaluation has to be made by clinician experts, right? So they are the only ones that can actually tell if their model could be useful, right, or could work in that specific setting. And to do that, we collaborated with EPFL, with the team led by Annie Hartley, who has built this open source medical large language model called Meditron, which is one of the many open medical large language models. And what we did was we created this platform to enable clinicians to assess Meditron and compare it with other models. So what was very, very interesting is that like doctors was really interested in participating to this initiative, and we managed to involve almost 20 departments in the CHUV with more than 300 clinicians that like spent hours in trying to challenge the model with some adversarial situation, right? Something that they've seen in their life where they expect this model to perform well, right? And this essentially helped us in sort of building an institutional culture on these LLMs, because by testing these LLMs, people started understanding where they are good at and where they are bad, when they hallucinate, why they hallucinate, and to better prompt, query these tools to get out what they need, et cetera, right? And this, I think it's a kind of a unique effort and very important that it's a prerequisite, before you can actually implement a large language model or a Gen AI platform in the hospital. So you need, to build trust, and you need the end users to understand and to learn and to sort of build this sort of vigilance, right, and ownership of their model. And then what we did is that essentially all this evaluation created, a huge preference data set around 8,000 question and answers from CHUV clinicians, right? Nurses and physicians. And then we reused this amount of data to align the model to the local preferences of the CHUV, because something that it's also very important to understand is that these models are trained on public data, on medical guidelines, and then every hospital, every country has its own way of doing medicine, right? Of course, it's all evidence-based, but the way CHUV works and the way CHUV manages also sepsis patient is different than Geneva, right? And you want a model that is tailored to your local context. And then we use this amount of feedback to create a new model that we call Meditron CHUV, which is a Meditron, but it's personalized to the way CHUV works. And currently we're in the process of seeing if in the end we're evaluating Meditron CHUV against Meditron and see if Meditron CHUV, that is something that we co-created with CHUV clinician, outperforms Meditron on this sort of adversarial cases, right? And for me, this is really the first step in a journey that will probably last a few more years, where essentially we have built this evaluation system by end users, this kind of vigilance system, and it's exactly what will allow us to have a strong governance of these models and to better leverage their potential, right? Because I mean, we have seen it many times, right? If you just dump a tool in the hospital, then people will not use it the correct way, will take bad decisions, and it's going to be more a risk than a benefit, right? Mm-hmm. So that's why we're taking this phase approach where the clinician is sort of at the center of this transformation. So is not passive, right? So and this is very important.
Yeah, thank you for this very deep overview, and it's really interesting to see how far you're already implementing and testing these tools. Maybe Marianna, if you want to react, I have follow-up questions, but please.
Yeah, I mean, we don't work with LLM, so I think we don't work so much with natural language. We work mostly with, omics, molecular data, and images. But just to say that I actually had the pleasure to be in the event when they launched, they closed the evaluation phase of this whole huge endeavor that the team went through, and I was there, to observe what they did, and a bunch of clinicians were also there. And it was really fascinating. I think what Jean Louis is doing is fantastic with Annie and with all the people of the team. It's really fantastic. Yeah.
Okay.
So I have two things I want to. So one small question on this, and then one last to turn to the future in medical research, and would like to do your opinion on this and your vision. One thing that I was thinking. So I also saw a recent LLM model for legal work in Switzerland by a startup called X-Nunc Intelligence. The product is called Silex. It's very interesting. It's also fine-tuned to match with the specific wording we have in legal work in Switzerland, and also deal well with translation, which is a huge challenge in Switzerland because you cannot translate anything. Some legal text judgment are in German, some in French, and you really need to fine-tune the model to have something that works well in this context. And they developed one part of the answer. Basically, you ask a legal question, you get the answer. And one part is about the uncertainty of the model. And I found this very interesting. So basically, there is, at the end of the answer, well, here is the gray zone. We are not certain about, the model is not certain about this. There are not precise rules here, or just evaluating the uncertainty about the quality and the precision, the answer that was found. And I was wondering if you had something in this direction as well with Meditron and what you're doing.
Yeah, I mean, I think large language model by themselves, they cannot measure their uncertainty, right? So it's at least not that I know of. Maybe yesterday there was a model that can do that, but essentially, I think there's something interesting is this concept of LLM as a judge, where essentially you have an LLM that generates some output. And then you have another LLM that sort of judges the output of or comparing, using multiple LLMs in a smart way, you can somehow measure that uncertainty, right? So if you, for example, you run the same question across 10 different LLMs, and then all of the 10 they say the same thing, then it might be, that the level of uncertainty is low. But if there's disagreement, right, then somehow your reply is not probably full confidence, right? So I think now and this goes a little bit towards this sort of agent systems, right, where instead of just using one LLM that does it all, right? So it's a system where you have different agents that will interact with each other, that will interact with external tools, like, for example, taking information from a RAG, so a database of documents, going on online search, and then we'll use this information as part of their context. So as part of the prompt, to better sort of narrow down the answer. And then this interaction of different agents is exactly, like this LLM as a judge is just an example where some LLM are judging, some LLMs are supposed to answer, and then there's this kind of interaction when one checks the other to provide, like some meaningful results to the end users. And I think in medicine, we're seeing this emerging, this trend emerging, which I think it's also a very good way of using LLMs in the end, because LLMs, we shouldn't take them as a source of knowledge, but more as tools that have this ability of interpreting natural language. So creating this very comfortable and easy to use interface with humans, but they also have the ability of sort of breaking down tasks and calling other tools to complement the information they get. To provide a more factual answer and more precise, right?
Mm-hmm.
And in medicine, there's a lot of groups that now are trying to build some sort of a medical assistant that is as an interface as an LLM, but behind the scenes we'll call a sepsis prediction model, maybe a digital pathology model, maybe a radiology segmentation, and then we'll have the ability to transform query into SQL, fetch data from the electronic health record system, and compile this and provide this information to the end users, which would probably what a clinician would do, right? Will try and search information here and there and try to compile all of this and take a decision. Mm-hmm. So I think there's really this evolution from just single LLM to agent, right? So and I mm-hmm. think this is really the way we should go. Yeah.
So that's a perfect transition for this last question, right? Where do you see the future? So Jean-Louis, you gave an outline already with this direction, at least with Gen AI. And Marianna, where do you see the future of medical research and your type of research, biological research also, going with all this breakthrough and technological change?
That's a very good question. I mean, I ask myself very often, what's going to be the next big AlphaFold moment, right, for our field. So I would say we are now pretty good at like ingesting data, understanding data. There's been a lot of interest in these big foundation models for, I mean, not LLMs, but, foundation models for pathology, for molecules, for proteins, for this, for that, for all different sorts of like, let's say, across different scales of biology, right? And people are trying to plug them in together in dubious ways. But I would say we're also like pretty good at like the field has really matured in like designing molecules. What we really don't know is what should we be inhibiting, right, in different diseases, or like what targets, what combinations. As I said, we really don't understand, especially the more we know and the more we profile, we really cannot make sense out of all this complexity. So I think in our field, what would be really transformative is to figure out ways to really understand exactly how and certain diseases like evolve and what we should be targeting, right? And so on one hand, I really believe in this direction of research. And another thing that I think is really fundamental across AI for health or medicine or biology or everything is that data, right? All these models depend on data. And, if the data is bad, the predictions are going to be bad, the models are going to be bad, right? So you cannot, I mean, in the case of LLMs, of course, it's again a huge topic of discussion based on which exactly public data these models were trained on. We probably don't know. There was a lot of like debatable practices followed in the terms of copyright and so on. I mean, this is a huge discussion on its own merit, right? But in the case of biology, what we've established is that we are lacking really good and informative data, especially for oncology. So we have a lot of fragmented data. You know, people like to measure things, but all different labs would measure their favorite molecules and their favorite panels and biomarkers. So we are a bit away from these like homogeneous, like massive data sets when it comes to oncology. I believe like in pathology, for example, which is one of the fields of medicine that has seen a revolution with foundation models, right? Which are actually very, very useful, the ones pre-trained on biopsies. One main reason that this happened is because literally every patient that had cancer had to have a biopsy taken. So we have millions of these images. Many exist in the public domain. Very often we have them also some annotation of these images and so on. So it was easier for people to pre-train using these huge data sets. And the same is true for molecules, right? So let's not forget how AlphaFold was made possible because there was a huge resource, which is PDB, the Protein Data Bank, which the vast majority of structures determined, ground truth structures in PDB were made possible because of public funding, right? This is something we should not forget. We are a bit away from that from oncology, and I think something that's going to be very transformative in our field is like investment in generating these data sets that the models can use, because there's just as little as you can do for, you know, with fragmented small data sets. You cannot generalize across diseases, across institutions. What you mentioned before actually about like interinstitutional variations is one of the biggest, if not the biggest, limitation in our field right now, because people measure these things with very sensitive machines, regardless of what they measure, if it's mRNA, protein, whatever. The technologies are slightly different, the protocols are slightly different, the people, the machines, even the exact day of the measurements. This is what we call like a batch effects, right? And this causes, I would say this is one of the most fundamental problems that we have. How well can we generalize in out of distribution data? That is, can be because of different sources. So I think we have really good modeling frameworks, and for sure there is a lot of things that we could you know, optimize and further develop and so on. But as long as we don't have, for as long as we don't have like good data, we are away from the big discoveries. So I really believe in an effort to generate that. Yeah.
Yeah, I just wanted to add a little bit on top of Marianna. I think data is crucial, right? We need high quality data. But this is also, you know, part of the culture, right? We need to educate people who collect the data to understand the importance of that, right? It's because you know, if we want to fully exploit the potential of AI, that this is crucial, right? So, and we are not the ones collecting the data. So this has to be a sort of collaborative effort. And then I think the other part that I wanted to mention is that there's a lot of focus. There has been a lot of focus so far in trying to build, you know, this or that model that can do X or Y, right? But I think this is also a little bit saturating somehow, and we need also to think on how do we translate this in actual use, because if you look at how many AI tools are currently approved by regulatory authorities as a device that can be used in clinical care, there's not like a huge number, right? And I think the translation aspect is what I think will keep us busy for the next years, right? Because the technology is there right now. Now we have LLMs, we can build agents, we can build foundation models. I think we can do very cool things, but if we cannot go to the bedside, all these things remains pretty nice and fancy in papers, right? But no actual impact. And I think this is, you know, there's a lot about human and AI interaction, understanding how people on the field work, how they could, you know, best leverage AI at which moment, you know, to do what, et cetera, and you know, the questions about the reliability, how do you work with regulators, because those models are living entities, right? They keep evolving because the data changes. You need to keep updating them. So also the whole regulatory framework of medical device needs to evolve, right? And be better suited to this kind of tools or technology. And I think that is where personally I would put more focus, in the next years to make this technology actually have an impact.